Hey everyone, and welcome. Today, we are going to crack the code on a fundamental algorithm that is just way more powerful than it looks. I'm talking about binary search. We'll cover the classic method, for sure, but you're gonna want to stick around because we're also going to reveal a second, kind of secret method that's a total game changer for a whole class of tricky problems. So let's just dive right in. But first, just picture this for a second. Imagine a dictionary, a physical one, that's 1,000,000 pages long, and I tell you to find one specific word. What's your gut instinct? Do you start at page 1 and just flip through every single page? Or is there a smarter, like exponentially faster way? That's the exact kind of puzzle that binary search just eats for breakfast. Okay, so before we get to the really clever solution, we have to understand this slow way first. The problem itself is pretty simple. You've got a massive, and this is key, a sorted list of items, and you need to find one of them. Now, the common sense approach is, unfortunately, also the most painfully slow one. This is what we call a linear search. You start at the very beginning and ask, is this it? Nope. Okay, how about the next one? Nope. And you just keep going one by one by one. I mean, if your item is at the very end, or worse, not even there, you literally have to look at every single thing. It'll get the job done, but wow, is it slow. In computer science speak, we call this O of n time complexity, and that n is just the number of items in your list. All it really means is that in the worst case, the time it takes to find your thing is directly tied to how big the list is. Got 1,000,000 items? It could take you 1,000,000 steps. We can do so much better than that. So let's level up. The secret weapon we have is that our list is sorted, and we can use that fact to our advantage to create something way faster, way more elegant, the classic binary search. The whole strategy hangs on something called a two-pointer technique. And don't worry, that sounds more complicated than it is. They're basically just bookmarks. You have a left pointer, L, marking the start of where we're looking, and a right pointer, R, marking the end. But the real hero of the story is M, the middle point we calculate between them. All right, enough theory. Let's actually see this in action with an example. Here's a simple sorted list of numbers. We're going to use this to walk through the process. And let's say our mission is to find out if the number 3 is hiding in here. And here's where that whole divide and conquer thing really kicks in. So we plant our left flag at the start and our right flag at the end. We find the exact middle, M, and we peek at the value there. In our array, the middle value is -2. Is that our target? Nope, we're looking for 3. But, and this is the light bulb moment, because the array is sorted, we now know something incredibly useful. This, right here, is the core logic. Our target, 3, is bigger than the middle value, -2. And since everything's in order, we know with 100% certainty that our target cannot possibly be in the left half. It has to be in the right half. So we can just throw away that entire left side. We do that by moving our left pointer, L, over to M plus 1. And just like that, boom, we've cut our problem in half. We just keep doing that, chop, 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 until we find our number. Okay, quick pro tip for you. You'll often see the middle calculated as just L plus R divided by 2. And that works fine for small lists. But if you're dealing with massive arrays, like with billions of items, adding two huge numbers like L and R together can actually cause an error in some programming languages. It's called an integer overflow. So a safer, more robust way to do it is with the formula you see on screen. It does the exact same thing, but it avoids that big addition, so it's a much better habit to get into. All right, so that was level 1, finding a specific value. But now for that secret I mentioned. This is the pro-level twist. It's a more advanced take on binary search that solves a whole different but super common type of problem. This is where we kind of flip the script. In a traditional search, we're asking, is the middle item my target? But in a condition-based search, we're not looking for a specific value at all. Instead, we're looking for the first time some condition becomes true. We're hunting for the exact point where things change. So, take a look at this. You've got an array that's all false, and then at some point, bam, it flips to true and stays that way. Our goal isn't just to find a true, there are plenty of those. Our goal is to find the index of the very first true. That transition point is what we're after. And you might think, okay, a bunch of trues and falses, so what? But this pattern is everywhere. Imagine a log of a patient's recovery. It might say sick, 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 and then one day switch to healthy, healthy, healthy. You're not trying to find a healthy day. You want to find the first healthy day. That's the turning point. This is the exact kind of problem this modified binary search is perfect for. So the code for this is slightly different, but it's so clever. Check this out. If our middle element is true, we know the first true is either at this spot or somewhere to its left. So we can't just throw this spot away. It might be our answer. So instead of moving our right pointer to m-1, we move it to equal m exactly. We're basically saying, okay, the answer is somewhere in this new smaller zone, including the spot we just checked. We just keep narrowing the window until L and R land on the exact same spot, which, you guessed it, will be the first true. So whether we're finding a value or a condition, the incredible speed of binary search comes from the same place. Let's dig into why this divide and conquer thing is just so powerful. Remember that O of n from the slow linear search? Well, binary search is O of log n. That's logarithmic time. And that log part makes all the difference in the world. It means that even if you double or triple or quadruple the size of your list, it only takes like 1 or 2 extra steps to find what you're looking for. It scales incredibly well. Let me make this real for you because this is wild. Say you have a list of 1,000 items. The slow way could take you 1,000 checks. Binary search, step 1, you're down to 500 possibilities. Step 2, 250. Step 3, 125. You get the idea. You'll find your answer in about 10 steps. Not 1,000, 10. That's not just a little faster, that is a whole different universe of speed. So here's the final head-to-head comparison. Linear search is slow, O of n. Binary search is blindingly fast, O of log n. And the best part? Look at the space complexity. They both use a constant amount of memory, O of 1. They don't get hungrier for memory as the list gets bigger. You get a massive speed boost for basically free. Okay, so let's zoom out. What's the really big idea here? What's the core takeaway? Well, the real genius of binary search isn't just about finding numbers in a list. It's a much bigger, more powerful problem-solving strategy. This is so important. Binary search isn't just for arrays. It's a way of thinking you can apply to any problem where you have a searchable, ordered range of possibilities. It doesn't have to be a literal list in your computer. If you can define a minimum possible answer, a maximum possible answer, and a way to check if any guess in the middle is too high or too low, you can use binary search, period. So now you have 2 powerful new tools in your toolkit. You've got the traditional binary search, which is perfect for finding that needle in a sorted haystack. And you've got the condition-based version for pinpointing the exact moment that things flip from one state to another. And that's really the thought I want to leave you with. This isn't just an algorithm. It's a mental model. It's a method for zeroing in on an answer by intelligently eliminating half the possibilities every single time. So the real question is, now that you have this superpower, what other problems, maybe even ones outside of programming, are you going to solve with it?